answers both of these questions in the negative. Why is this the case? Newton left the impression that there were no assumptions in his physics which were not necessitated by the experimental data. This occurred when he suggested that he made no hypotheses and that he had deduced his basic concepts and laws from the experimental findings.
Then laws.
Were this conception of the relation between the physicist's experimental observations and his theory correct, Newton's theory would never have required modification, nor could it ever have implied consequences which experiment does not confirm.
Experimental.
Being implied by the facts, it would be Introduction 13 as indubitable and final as they are. In 1885, however, an experiment performed by Michelson and Morley revealed a fact which should not exist. Were the theoretical assumptions of Newton the whole truth? This made it evident that the relation between the physicist's experimental facts and his theoretical assumptions is quite other than what Newton had led many modern physicists to suppose. When, some 10 years later, experiments on radiation from black bodies enforced an additional reconstruction in Newton's way of thinking about his subject matter, this conclusion became inescapable. Expressed positively, this means that the theory of physics is neither a mere description of experimental facts nor something deducible from such a description. Instead, as Einstein has emphasized, the physical scientist only arrives at his theory by speculative means. The deduction in his method runs not from facts to the assumptions of the theory but from the assumed theory to the facts and the experimental data. Consequently, theories have to be proposed speculatively and pursued deductively with respect to their many consequences so that they can be put to indirect experimental tests. In short, any theory of physics makes more physical and philosophical assumptions than the facts alone give or imply. For this reason, any theory is subject to further modification and reconstruction with the advent of new evidence that is incompatible, after the manner of the results one of the Michelson-Morley experiment, with its basic assumptions. These assumptions, moreover, are philosophical in character. They may be ontological, i.e., referring to the subject matter of scientific knowledge which is independent of its relation to the perceiver, or they may be epistemological, i.e., referring to the relation of the scientist as experimenter and knower to the subject matter which he knows. Einstein's special and general theories of relativity modify the philosophy of modern physics in the first of these two respects by radically altering the philosophical theory of space and time and their relation to matter. Quantum mechanics, especially its Heisenberg principle of indeterminacy, has been notable for the change it has brought in the physicist's epistemological theory of the relation of the experimenter to the object of his scientific knowledge. Perhaps the most novel and important thesis of this book is its author's contention that quantum mechanics has brought the concept of potentiality back into physical science. This makes quantum theory as important for ontology as for epistemology. At this point, Heisenberg's philosophy of physics has an element in common with that of Whitehead. It is because of this introduction of potentiality into the subject matter of physics, as distinct from the epistemological predicament of physicists, that Einstein objected to quantum mechanics. He expressed this objection by saying, "God does not play dice." The point of this statement is that the game of dice rests on the laws of chance, and Einstein believed that the latter concept finds its scientific meaning solely in the epistemological limitations of the finite knowing mind in its relation to the omnicomplete object of scientific knowledge and, hence, is misapplied when referred ontologically to that object itself. The object being per se all-complete and in this sense omniscient, after the manner of God, the concept of chance or of probability is inappropriate for any scientific description of it.
It's impossible.
This book
There
is
is no
important because
chance.
it contains
It's all
Heisenberg's
planned.
answer to this criticism of his principle of indeterminacy and of quantum theory by
It
Einstein
is
and by others.
determined already. We just don't know
In
how.
understanding this answer, two things must be kept in mind. The aforementioned relation between the data of experimental physics and the concepts of its theory. 2. The difference between the role of the concept of probability in A. Newton's mechanics and Einstein's theory of relativity and in B. quantum mechanics. Upon I. Einstein and Heisenberg, and relativistic mechanics and quantum mechanics, are in agreement. It is only with respect to 2 that they differ. Yet the reason for Heisenberg's and the quantum physicists' difference from Einstein on 2 depends in considerable part on I, which Einstein admits. I affirms that the experimental data of physics do not imply its theoretical concepts. From this it follows that the object of scientific knowledge is never known directly by observation or experimentation, but is only known by speculatively proposed theoretic construction or axiomatic postulation, tested only indirectly and experimentally via its deduced consequences.
Maybe.
To find the object of scientific knowledge we must go, therefore, Introduction 15 to its theoretical assumptions. When we do this for A. Newton's or Einstein's mechanics and for B. quantum mechanics, we discover that the concept of probability or chance enters into the definition of the state of a physical system, and, in this sense, into its subject matter, in quantum mechanics, but does not do so in Newton's mechanics or Einstein's theory of relativity. This undoubtedly is what Heisenberg means when he writes in this book that quantum theory has brought the concept of potentiality back into physical science.